So here's the video where I wanted to give you some help with the homework because we didn't get quite up to ionization and how you can determine whether or not a functional group is ionized at a particular pH. So I'm going to grade that part of the exercise rather gently. Here's some tips for you. So there's a program called ACD Chem Sketch, and it's free and it's great. I use it all the time. If you have a different program that you've used that you're comfortable with for drawing chemical structures, just use what you know and what works for you. But for those of you who don't have a ChemDraw program, this one's pretty nice, and I'll put the link for this on Canvas for you. So here's a quick tip. I told you use PubChem for the homework. Let's go over to PubChem. Here's PubChem, and you could put in, I put in glutamate because it is an ionizable amino acid, has an R group with a carboxylic acid group. So you could search for glutamate, and here it comes up, and if you click the record for glutamate, you can see all of its other names, and hopefully this is going to link over quickly. There we are. It shows you the structure, it talks about safety, gives you all the different names, molecular weight, everything is here. Anything you would want about glutamate, anything you want to know, it's here. But the reason that I'm showing you this is because you can take the smiles, right? The canonical smiles, and you can highlight them. And you can copy them. There, I did it that way. I used my keyboard shortcut Control-C, but if you're on a Mac, I don't know how to do that on a Mac. Now you can come over to Chem Sketch, and you can do Generate Structure from Smiles. And you can put your smiles in. It saves your last bunch of smiles. So that was probably, I don't know, something else I was working on. There you go. There's your glutamate. And you can click, put it anywhere you want. So there's your glutamate. And if you want to move it around, you can move it around. There's a way you can spin it and turn it. There we go. I love this program. It's relatively intuitive. And it didn't take me too long to learn my way around here. I still get stuck sometimes, and you know what? That's okay. The point is, when you're learning a new technology, don't give up. We're going to look at two groups here in our glutamate. So we didn't get there yet with the structure of the amino acids, but we have here, and I'll use the pointer, an alpha carbon. So here is our alpha carbon, and this alpha carbon has 4 things coming off of it in every amino acid. It has an amino group here, it has a carboxylic acid group here, and then it has a hydrogen not shown, and then we have our R group, which is this over here. So we're going to look at the carboxylic acid groups on glutamate, and these groups are ionizable. This would be the alpha carboxylic acid group, and this would be the R group carboxylic acid group. We also have an ionizable group here in the amine, and this can go from a nitrogen with 2 hydrogens to a nitrogen with 3 hydrogens, in which case it would adopt a positive charge on the nitrogen. So these groups, the carboxylic acid groups, are protonated as you see them, and this amine group is deprotonated as you see it. These groups are ionizable, so they can add or lose hydrogens based upon the pH of the solution. And we're going to go over all of this in much more detail next week. So in glutamate, we just saw that there's an amine group, and that amine group can gain or lose hydrogens based upon the pH of the surrounding solution. And we also saw 2 carboxylic acid groups in glutamate. One of those carboxylic acid groups comes off of the alpha carbon, which you could think of the alpha carbon as the heart of the amino acid. And then we have a carboxylic acid group that is part of the R group in glutamate. And carboxylic acids can gain or lose hydrogens based upon the pH of the solution. Now, the protonated to deprotonated forms, right, whether we're dealing with this group or this group, the protonated or deprotonated forms, the relative ratio of them depends upon 2 things: the pH of the solution that they're in and also the pKa. So we will cover much more of this in detail next week. But just to get you through for now, I'm going to show you an easy way to figure this out. As you see here, the nitrogen is deprotonated. If we gain 1 hydrogen, it would be NH3 with a positive charge on the nitrogen. Note that the number of hydrogens are different than this example over here, because in glutamate, that nitrogen is making a covalent bond to the alpha carbon. So for nitrogen, whether or not it has a positive charge, it's all about the number of bonds with other atoms. As a quick reminder, before I show you the very easy way to remember whether something is protonated or deprotonated. Protonated means the hydrogen is present. Deprotonated means the hydrogen is gone. And what is a hydrogen, right? But a proton with an electron. So sometimes we think about, ionized hydrogens. They're just protons, right? So an ionized hydrogen, an H+, is just a bare naked proton. So that's why we can talk about protonated or deprotonated. So you can look up the pKa values for the different functional groups in a molecule. Warning, here's a warning. A pKa for a carboxylic acid group on the R group of glutamate is going to be different than the pKa for a carboxylic acid group coming off the alpha carbon of glutamate, because the pKa's of these functional groups is highly dependent upon the local electronic environment of that functional group. So anytime you're trying to determine whether or not a functional group is ionized or deionized at a particular pH, you really should look up the specific pKa for that molecule if it's known. So to sum this up and to give you the bottom line, just to get you through for right now, if the pKa of a functional group is above the pH of the solution, then the functional group in question, is protonated. If the pKa is below the pH, then the group is deprotonated. And I should say, if the pKa of the functional group in question is below the pH of the solution, then the functional group is deprotonated. In some cases, when the group is protonated, it may have a positive charge, like this amino group here. If the pKa is below the pH and the group is deprotonated, it may have a negative charge, like this carboxylic acid group here, which we refer to as a carboxylate because it's deprotonated.